let's see. Okay. Looks like we have 7 people so far, so let's go over this. So we got Minthi, good morning to you. Alexis Valdez, good morning. Epi Garcia, Wen Yu Sang, Sheila, Oriana, thank you, good morning. Rebecca, good morning. Carol, good morning. And Jesse Soto, good morning. So we'll get more people coming in. David Flores, good morning. And let's actually talk a little bit about some of the things that I've upgraded there for you guys. So for example, let's take a look. Let's go to um, our browser here. And alrighty, we got the browser. And let's go to our class here. Oh, wrong one. Seems to be a little bit of slow this morning. So let's go to Math 262. And we're going to go down here to the online transition. So let's talk a little bit about this so that we're up to date and we know this is the stuff we've been working with, integration by trigonometric substitution. And then over here we have trigonometric substitution 1, trigonometric substitution 2. These are the YouTube videos that we have posted already online. And then over here I have some examples, like I mentioned, that I was going to give for you guys. And this is the second example of additional question, sorry. And this is the one that we started with yesterday. And again, I'm going to remove that stripe. I have a new scanner coming in, so we're going to rescan these things and remove that stripe from the old scanner. And this is actually the work from everything that we did, the additional examples from yesterday. We started this question, and I finished this question off for you guys. And as you guys can see, yes, there's some work there. But it's nice, predictable work, some algebra using identities. I want to go here and say, you know, when you get down to sine 2 theta, we're going to always use the identity 2 sine theta cosine theta. So that's right over, I should say, oh, maybe we should focus on that. Where is it? Yeah. Right up in here in red. So I want to point out that happens quite often. And that's when you have sine 2 theta, because the right triangle you're using is only in regards to theta. So anyway, so I want to point a little bit about that out. And as you guys can see, there was some work here. And this is the final answer for that one we tried yesterday at the very end of our lecture. And similarly, I said, okay, let's try to do another one. And this next one, very similar. It involves a quadratic under a radical. And again, this is what we'll do when there's quadratics there. Let's focus on the middle of the page there. This is what we're saying. We complete the square. So I did go through the process of completing the square there for you guys in this next example. When we pulled out that -1 here, and then you complete the square with the quadratic, because you want a positive value for a. And so I completed the square there for you guys on this one. And as you can see, what it really becomes is 9 minus x, 9 minus in parentheses that x minus 2 squared. So going through the same exact process, okay, we get a integral where you have to use trig substitution, and it turns out it's case 1 there, okay? And it's no longer x, it's u. So I'm just going through, skimming this example and saying it's going to go through the same process. You get a trig integral, and this trig integral now simply becomes the integral of cosine squared theta. So there it is up there. And the rest is done in the very, very similar way. So I'm going to scroll down and show you guys here. Yes, you could go back and look at this PDF file for you guys. It's all written down for you. And then I'm going through this, scrolling through here. But I showed all the work, and like I said, I'll put some additional examples every day for you guys that are written down and you could review, and it's based on everything that we did on the lecture. So I'm just going back here and showing you via our browser that I am placing those additional examples to the right over here. And the first lecture had these corresponding examples. Second lecture has these additional examples. And then today, we're going to work on the integration by partial fraction decomposition. Okay, so there's another technique, and I'm going to ask you guys here, let's see if you remember partial fraction decomposition. Okay, in pre-calculus, you study partial fraction decomposition. Essentially, in partial fraction decomposition, what you do have, and I'm going to go to something like this. This is on my webpage. So when we go to our iPad, right? I'm going to activate the iPad now. And let's see, passcode. Here's our iPad. So I'm going to ask you guys if you remember from Math 260 pre-calculus. I'm going to minimize this so you can't see it. Partial fraction decomposition. When and where do you use it? What's its purpose? Okay, that's an original question for you guys. What's the purpose behind partial fraction decomposition, right? So I know there's a bit of a delay for you guys to answer, but I want to ask this morning, when from pre-calculus or whatever we call that, math analysis, when do we use partial fraction decomposition? What's its purpose? Right? Okay. Well, that's okay. We all have to wake up, even myself, and hopefully we can do this, waking up business, not make any mistakes today. So, all right, let's try to take a look here. Here's what I have written down for you. If you start to look at those notes, integration by partial fraction decomposition essentially is you have what's called a rational function. Now, a rational function simply is a function that is a fraction, and we designate that as r of x. So r of x, we like to say here, is p of x over q of x. Now, p and q are very special. P and q need to be what we say is polynomials, both of them. So you have a polynomial on top, and you have a polynomial on the bottom. So both p and q are both polynomial functions. Now, technically, if you guys want to know the real definition of a polynomial, okay, here's how we describe it in general. That is an xn plus an minus 1 xn minus 1 a1x plus a naught, where all the a's with the subscripts, right? Like an minus 1, a1, and a naught, these are called constants, or just really real numbers. And you can also see the x here, xn minus 1, and so on, all the way down to x. Those are the variables, and n is the degree of the polynomial. So we write this as the degree of n. I'm sorry. Coffee doesn't kick in. The degree of the polynomial is n, and that's how we write it. Degree, we write it in functional notation. So that's the highest power of your polynomial. Now, similarly, we can describe q this way, but the point is you have a degree of n, and you also have a degree of q, whatever that could be. And sometimes we just say that's m, because we can also describe maybe that q of x, if you guys remember, as bm xm plus bm minus 1 xm minus 1 all the way down to b1x plus b naught. And similarly, you have the bm minus 1, and so on, b1 and b0. These are also constants, or we simply say they're numbers. Okay, and so you have the degree of m now, looking at the highest power. That's the degree of your, this is the m. It's the degree of your q function, right? Your polynomial q in the denominator. So anyway, this is starting to describe here what's known as a rational function. So we're going to be integrating rational functions now. And you've already known how to do some of them. So you have r of x there, I wrote in our notes, which is really the integral of p of x over q of x dx, where both p and q are polynomials. So here, this is what we started with in terms of our notes, saying, okay, integration by partial fraction decomposition. And let's get to the reason why, sort of, or give you an example of, why we would use this technique. But before we do that, let me point out some very important kind of thing that happens. This is a very special thing. Now, if you notice, like for the trig substitution, for trig sub, we had a bunch of cases that we looked at, all these different cases. You had case 1, case 2, case 3. So you're looking at different cases to decide what approach you should take. And that's going to happen here as well. We're going to have to look at cases and decide what approach we should take. So the first kind of thing I want to start the lecture with, it shows up. I want to remind people that this does happen. They're going to probably throw this at you guys. To give you a quick example, this is really what you do in this particular case, and I'll talk about that. You have x squared plus 2x plus 1 over x minus 3 dx. So notice we have a polynomial in the numerator, polynomial in the denominator, and this is a special kind of case. Let me write this down. I want to point out this detail. The degree of the numerator, p, and if you just see x, that power is 1, so that the degree of the denominator, okay, that means the degree of p is bigger than the degree of q. And I'm going to add this greater than or equal, because when you have even an equal power there, I'm going to make this big recommendation that you do. Here's what you guys do. You're simply going to divide. And this happens a lot in your integration career, that if you have the same powers, divide. If the numerator is bigger than the denominator, well, then you divide. You divide these polynomials. And I'm going to show you the benefit. You say, well, why do I divide? Well, let's take a look. Now, the division here, as you guys already know, I kind of joke and I say things to you like, okay, do you guys remember how to divide? Dividing polynomials. Now, this is where I come in and I say all those, cute little remarks. I guess, okay, contact your younger brothers and sisters in beginning algebra, right? And have them tutor you while you're Calculus 2 students. And it's kind of funny. But it's not that funny, but it's actually true. You have to do a lot of review, as we've been preaching, and I've been preaching for a lot. There's a lot of review you do. And it's good for you because it makes you stronger. It makes you more competent. And, it's a lot more rewarding. But anyway, this is a beginning algebra division question. And so if you remember there, and I do have this on my website. So darn, maybe let's go back here. How about if we do this? Well, you guys know my website. I won't do that. I do have a beginning algebra portion there, videos that does have division for you guys. So if you had a review, right, or since we're home, it's a good chance to turn this all into a positive. review that. And if you guys need, need the links, just let me know. I'll provide the links there for you guys. But yeah, you're going to just simply divide here by using techniques from beginning algebra. Okay, so here's where we start. We got x squared over x. Remember that? X squared over x gives us an x. And I put that answer above the same term. And the same term meaning 2x is linear first power. I put that above the 2x. And then if you guys remember, you multiply, right? So you multiply this x with the x minus 3, and it gives you x squared minus 3x. And let me get rid of some of this here. Third step is we subtract, right? We subtract, which really changes these signs. And so now we do our subtraction, which is x squared minus x squared is gone. 2x plus 3x gives you a 5x. So I got 5x here. Now I bring down the 1. So this is the 4-step process in dividing. And so after we do that again, we say, okay, we repeat the process, meaning 5x divided by x. And we say 5x over x is 5. Now that's a constant term. That term goes above the constant here. And you repeat 5 times x minus 3 gives us 5x minus 15. We subtract now, or really change the sign. And so we get 5x minus 5x is 0, it's gone, and 1 plus 15 gives us a nice 16. Okay, here's our division. Now, we have to know what we're looking at. What does this actually mean, if you guys remember? Well, this means the following. This is your quotient. This is your remainder. This is what's doing your dividing. So your fraction, which is improper in a sense, right? X squared minus 2x plus 1 over x minus 3, we can write this as a mixed number, quotient, remainder, divisor. And really the definition of a mixed number is that you're taking a whole number part called q, and you're adding it with a fraction. That's what this actually equals here. So at the end of the day here's what you guys get. This equals x plus 5 plus the remainder 16 over x minus 3. Now, this isn't partial fraction decomposition. This is simply division. And you might say, well, how does this benefit us? Well, go back. Your fraction here can get replaced with the quotient plus remainder times what's doing the dividing. And, I get a little, a little OCD there. I want that to be a lowercase r, so it's now consistent, okay? But we're going to replace that integral here. And this is what it gives you. X plus 5 plus 16 over x minus 3 dx. Now, this is a lot easier to integrate, okay? This is very easy to integrate because by properties of integrals, I guess I can do it this way. How about if we try this out? This is by properties, okay? Meaning the integration of a sum is sum of integrals. We can also pull out our constants. So I can say this is the integral of x dx plus an integral, let's say 5 dx, plus an integral of 16 over x minus 3 dx. And similarly, we get the integral of x dx plus 5 times the integral dx. Pull out your 16, we get 1 over x minus 3 dx. So as you guys can see here, just using properties now, we can answer this question. And the integral of just x, well, what's that integral? Do you guys remember? That's 1/2 x squared. That's going to be power rule for integration. The integral of dx is x. And here the integral of 1 over x minus 3, we know is natural log absolute value x minus 3. So putting all this together here as a final answer, we have 1/2 x squared plus 5x plus 16 times the natural log absolute value of x minus 3. Okay, so here's what you guys have as an answer. Now, let me go back really quick, and maybe this is not the point, but how about if I start to do something like this? Maybe I'm going to make a quick remark. Let's get rid of these. The power 2 is there. Just as an aside, just as a note, maybe you guys want us to plug in some values, right? This is my antiderivative. Remember that? And, yesterday we had some questions about what about some limits? Why don't we add a little bit of limits to a little bit of arithmetic, right? Well, we can. Let me just kind of remark about this. If I want to put some limits, I got to be careful here, right? Because this is getting into our future. So this is why I want to talk a little bit about it. X minus 3 here, that denominator, this function, this rational function is discontinuous at x is 3, right? X can't be 3. Let me remove that. Okay, so we know x can't be 3. So if I want to put a little bit of limits here, I mean, I could do the proverbial 0, 1, and that, is going to be something that people may want to look at. But what if I just said, let's try negative 1, 1, just for fun, just to remark, okay? So if we put these limits now, 1 to negative 1, notice, is this function continuous in that interval? And the answer is yes, because the only point where this function is discontinuous is at x is 3. So just want to remark about that. Okay. So now if we said, okay, let's try this in terms of limits, just for fun, because you guys had the request yesterday. We're going to have to evaluate this, right? From x is negative 1 to positive 1, which means the value is f of 1 minus f of negative 1. And so in that case here, we say, oh, this is 1/2 times 1 squared plus 5 times 1 plus 16 natural log 1 minus 3. This is f of 1. Now be careful. We have to subtract f of negative 1. So that's 1/2 negative 1 squared, 5 times negative 1, 16 natural log absolute value of negative 1 minus 3. So that's plugging in the first case, right? Let's maybe change some of these colors here. You guys start to see how weird this can get, right? Here's 1. There's your 1s. You guys know this. And negative 1. Here's my negative 1s. Okay. That's what we're doing. We're just going to do a little bit of arithmetic here this morning. 1/2 plus 5 plus 16 natural log absolute value of negative 2 minus, be careful, this is also going to be 1/2. Now it's minus 5 plus 16 natural log absolute value negative 4. And I'm going to do a couple of things now. So let's take a look. This is going to be 2. This is 4. And then I'm going to distribute the negative sign. Okay. All right, let's take a look. I'm sorry about that. Let's take a look at these here. We got some questions here. I got that bell. Okay. David Flores, good morning. Winwar Toon, good morning. Brenda, good morning. How Chen Yu, good morning. Kirby, good morning. Austin, good morning. And Kirby again. Does the answer still have a plus C? Did we? The answer, yes. Yes, Kirby, thank you. The answer is back here plus C. Right? Kirby's question. Absolutely. Thank you. Let's put that here so people can know. Thank you for catching that, Kirby. I was so interested in putting limits here, I didn't put the C. So we put these limits here, And anyway, thank you. I apologize I didn't get to that sooner. So let's take a look. Let's see what this is going to give us here. 1/2 plus, I'm going to say 5. Well, how about we'll keep it that way. Plus 16, natural log of 2 now. Let's distribute. And I'll put it down here. Minus 1/2 plus 5 minus 16, natural log 4. So if we notice, we're going to have some cancellation here. Gone and gone, right? And then this is going to give us 10 plus 16, natural log 2 minus 16, natural log 4. So some people are going to look at this and they're going to say, okay, well, what do I do now? Well, here's what I'm going to suggest. If you look in back of the book, they're going to factor out the 16, natural log 2 minus natural log 4. Okay, so this is a little bit of algebra. Now, here's what's going to happen here. Just like yesterday, what happens down here? We're going to use here properties of logs again. This is going to be really, it's called the quotient rule. So this becomes natural log of 2 over 4, which is really 1/2. So when you look in back of the book, you might say, do I see 10 plus 16 natural log of 1/2 as an answer? Yes. So I'm just giving you a little bit of, a certain case for rational functions where the degree of the numerator is at least as big as the degree of the denominator, meaning simply do your division, your division algorithm from, beginning algebra. And again, like I said, and Kirby was right, we have to put the plus C, but the second they give us limits, we have to apply the limits. And up here, upper limit in green, lower limit in orange, and this is the application of some of the limits. Since I had a request there from the other day, somebody wanted to see some limits there. So we're going to honor that, and I'm going to show you, because in our future, we're going to apply more limits, and we're going to do a little bit more arithmetic here, but this is essentially what you do. And as you guys can see, what I've kind of opted in some of our examples in class is to avoid some of those limits, only because we can get a little more technique in as we lecture. Okay, we get a little more of what to do, and then I trust you guys can do some of the arithmetic, but we should see some arithmetic every now and then. So it's not a problem. Anyway, this is what you do in that first case, but it's not partial fraction decomposition. So partial fraction decomposition, though, if we want to start with some of that, we have to know and write this down. I abbreviate this PFD, partial fraction decomposition. Now let me describe what this really is. That's when we write a fraction, rational function, as a sum and difference of what I'll describe as simpler fractions or rationals. That's essentially what that is. And if I go up here and I say, okay, did I write this down? Let's see. We use partial fraction decomposition. When integrating rational functions, essentially we are writing a rational function as sums and differences of simpler rational functions. And the reason we do that is, of course, so that we can integrate. That's the whole idea. They're easier to integrate. And again, like trigonometric substitution, we just need to consider cases now. So the focus at this point is in the process of PFD. First case that we want to focus on is what's called linear factors. And it's really known as distinct linear factors. Distinct meaning different. So if I say your denominator function, q of x, is a product of distinct, different linear factors. Now linear here, let's write the meaning of linear. It's something you guys, know. Linear is anything of the form ax plus b, like a linear equation. right? In algebra, that's what they mean. And distinct means, again, different. That phrase is the same. So we're going to look at situations where you have distinct different linear factors. And then I have here such as x times x plus 1, or simply x minus 1 times x plus 2, or 2x minus 3 times 4x plus 7, or really x times x minus 3 times 5x plus 2. Those are in your denominator. So we're going to look at an example here of what we call case 1. Okay. Yep. Thank you, thank you, Marbella. You can't see because I'm actually reading from that form. But yeah, now you can see. Oh, I see your point. Yeah, thank you. Okay, okay, I see your point. Yeah. So anyway, here is what we're talking about: your distinct linear factors, different. So case 1. I'm going to look through my notes. We're going to find a good example. Here's what they mean. Okay, here's an example of what we call case 1, and here's what we're talking about. If we look at the bottom here, x plus 4, well, of course, that's again what? Linear. It's of the form ax plus b. Of course, a is 1 here and b is 2, but that's the point. We have another distinct, different linear factor, and that's going to be 2x minus 1. Here, yes, a is 2, b is negative 1. But the point I'm trying to make here is these are what we call distinct linear factors for your denominator. And so what we're going to try to do here, if you guys remember from partial fraction decomposition, the fraction x over, and let's write this way, so, hopefully you guys recall, how did you guys do this in pre-calculus? How did you do partial fraction decomposition there, right? This is a review, really, again, that process you guys want to go back and review, because here you have a fraction, and here's what we're going to do. For every distinct, different linear factor, you're going to write a, that's going to be a constant, over that first linear factor, and then plus b over the second linear factor. That's 2x minus 1. So a is a constant, ladies and gentlemen. B is a constant. So this is how we start our partial fraction decomposition with distinct linear factors, case 1. And here's going to be our task. Here's what we have to do. What's the value of a and b? What are those constants? And this is what we have to find. If we can find those values, then we can replace this more complicated fraction, rational, with the sum, in this case, of two simpler rationals that we can actually use for integration. And that's the whole idea. So a big part of really what you do is you're just going to go with a format of how to set up these factors. But the real work is going to try to be finding there the values of A and B. That's where you're really going to have to put some time and energy. So I don't know if this clears out some of the cobwebs from some of you guys, but this is where this is at. Now, let me express how we do this here. There's a couple of ways. If you notice on the right side here, we have a sum of two different fractions. Now the denominator x plus 4 is thought of as being prime, and the denominator 2x minus 1 is thought of as being prime. So I'm going to say to you guys, we're going to start here by doing this. We're going to add these fractions. And when you add fractions, let's recall, yes, they have different denominators. They're unlike, you follow the process for adding unlike fractions. But you do have a shortcut. If you guys remember the shortcut for adding fractions, and in some cases this is very valuable. This is one of the case. If you guys remember, how do we add fractions by the shortcut? Remember, we cross multiply, and we multiply here horizontally. So this gives us BD in the denominator and AD plus BC in the numerator. So here you go. In our case, what that means is we have A times 2x minus 1. And let me do this here. Let me write it over here. Let me be complete for this first example because you guys should see this. Here's what we get, right? This is the left side, and by the right side, we get the following. Using our shortcut, we're going to get the constant A times 2x minus 1 plus the constant B times x plus 4 over x plus 4 times 2x minus 1. So I'm writing my left side and my right side. I'm using the shortcut for adding unlike fractions here. Now I'm going to use a little bit of logic. Here's the logic here, okay? Notice the left fraction and the right fraction have the same denominator, okay? They have the same denominator. So I'm going to say this to you guys. If you have two fractions that are equal, A over B equals C over B. Two fractions that are equal. I mean, I could do a little bit of algebra. I can multiply both sides by B, and if I do, the denominator for B goes away, and I end up with this A equals C. So here's my point to you guys, right? Here's what I just said. Algebraically speaking, isn't it true? Multiply the left by B and the right by B, and I get cancellation of the B denominator, right? This goes away, and we're left with AC. That's what I'm saying here. So let's get rid of all this. So the point I'm making here is that since the denominators are equal, see this here? They're the same. What that forces us to conclude is my numerator, x, a 2x minus 1 plus b, x plus 4. This has to be the same. And this here, ladies and gentlemen, is really where all the work is going to come in. It's not in setting this up. You can set this up pretty fast. However, this is where the work comes in. We have to determine, again, what is A and B. And there's various ways to do this, okay? So I'm going to remark about the various different ways. So let's see, how can we start to do this? Well, let's stop and think, because there's three ways. There's an easier way, there's a difficult way, there's just different ways depending on your skill sets here. But I'm going to try one way. Let's try doing this. Here's our first method. The first approach to finding A and B, what I can do is simply do a little bit of algebra, meaning I'm going to distribute. I'm going to get rid of those parentheses on the right side. So I have x equals 2ax minus a plus bx plus 4b. Okay, I just distributed here. That's what I did. And then I'm going to gather the like terms, meaning my linear terms here. Because it has an x and an x. I'm going to gather them together. And if I do that, I'm going to leave the constants here separate. So here's what you get. X equals 2ax plus bx minus a plus 4b. And I'm going to factor out the x over here. Okay? So my x here becomes 2a plus b, okay, x minus a plus 4b. And so this is an equation here. Let's double check to see if our algebra is okay. It looks like it's okay. So let's stop and think here, right? The left side equals the right side. This has a lot of meaning, believe it or not. This has a lot of meaning. What that means here is, right, the left side equals your right side. Notice what's on the left. You have an x term, you have an x term here. The constant in front of this left x is 1. So what that means logically is what has to happen is 1 has to be the same as the value of 2a plus b. So we're going to write that down. We know 1 equals 2a plus b. Similarly, you might say, well, what does it mean about, what does that actually mean? Let me erase some of these things so we don't get confused. So you might say, similarly, what does that actually mean about the constant term? Meaning, what does that mean about the negative a plus 4b? What does that negative a plus 4b actually equal? And I'm going to put this down here. Negative a plus 4b does equal something. We want to know, what does it equal? Negative a plus 4b. Anybody have a guess? On the left side over here, right, do we see any numbers? Is there any values like a 3 or a negative 6 or an 8? Do you see any number on the left? Right? The answer should be what? No, there's no numbers there. I'm going to put a number. The only number I can put is 0. Because 0 plus 1x, or simply 0 plus x, is just the x. See, I can add 0 to anything and it doesn't change the answer. So what that means is that 0 is the same as what we wrote over here. Negative a plus 4b. Thank you, Winmore. That's 0. So what you guys now have is this. This is what you have. Let me clarify. 2a plus b equals 1. Negative a plus 4b equals 0. And now I'm going to say this to you guys. Here is what I mean. Most of the work is going to be finding your constants. So what you guys remember from pre-calculus, pre-calculus or math analysis is we have what's called a system of equations. Okay, we have 2 equations and 2 unknowns. The unknowns are a and b. So this is a 2 by 2 situation, right? 2 equations, 2 unknowns. Now you might say to me, well, how do I solve this, Mr. Judge? You solve this by doing what? You solve this various ways. You can go back to even beginning algebra again. And in beginning algebra, you solved these kind of equations. This is a system of linear equations. You had the addition method, the substitution method. I suggest you don't use the graphical method. But substitution or addition to finding a and b is what you guys do. And you might do a lot of that here now. So here's another sort of opportunity to review to solve a system of linear equations, right? So this is a system. Now, if you take the other courses, you might say, well, I learned Kramer's rule. I learned how to solve this by, an augmented matrix. I learned the matrix method. Can I do that? And the answer is yes. So you're going to need to review how to solve a system. Now, I'm just going to use really simple beginning algebra, personally. So here we get 2a plus b is 1, and I'm going to multiply the second equation by 2. So I get negative 2a plus 8b equals 0. So if you guys remember by that method, I just multiplied this by 2. And so what you now end up with is a nice equation where, by the addition method, of course, we add what? This is the addition method. We add the left sides together, sum it with the right sides together, and you notice your 2a minus 2a here, this goes away. You're gone. Then you get a b plus 8b, that gives you 9b. And 1 plus 0 is 1. So since 9b equals 1, what you can say is b equals 1/9. That's where your work is. So we found one value. And at this point, if you guys do recall, from beginning algebra or even from pre-calculus, because you do solve these systems too, how do you find the a value? Do you guys remember? How do we get a? What are you going to use? That's called using what? Back substitution. So to get the a value, you got to use back substitution. Back substitution means plug the value for b back into any of the two original equations, the first or the second one. It doesn't matter. So at this point, you might say, okay, I'm going to use the first equation. 2a plus b is 1. And yes, we plug back in what? B being 1/9. So we get 2a plus 1/9 is 1. And we have to solve for a. Right? That's an a, sorry. Let's make sure it looks like an a. So you say, well, how do I do that? Well, let's subtract 1/9 from both sides, right? And then we end up with 2a is going to be 9/9 minus 1/9. Or 2a is going to be 8/9. And you may say, well, how do I solve for a? Divide both sides by 2, so we have cancellation here, right? So a is going to be 8/9 divided by 2. 8/9 times the reciprocal, 1/2. And then you might say, oh, do I simplify my fraction? Sure, you do. So now the value of a here is 4/9. This here is what we need. This here is the two values we need. So let's go back. A is 4/9, and then b is 1/9. Partial fraction decomposition is this process that was learned in pre-calculus. So, okay, you say, okay, Mr. Judge, what's so important about finding those a and b values? And I'll say it goes here. This is what's important. The value of a was 4/9. The value of b is 1/9. Okay, so this here is what we need. So that our integral now, this original integral, really becomes the following. Let's see if we can, I don't know if we can fit this in, but we're going to try. Let's do it right here. This integral really is 4/9 over x plus 4 plus 1/9 over that 2x minus 1 dx. Okay? So now with properties of integrals, right, we know the integral of a sum is sum of integrals, and we can pull out some constants. So let me go all the way down here. I apologize if this makes you guys dizzy. Okay, here's what this means. For ninths, 1 over x plus 4 dx plus 1/9 integral 1 over 2x minus 1 dx. This is why we did what we did, okay, by using properties. Now, as you guys know, this here is easy, and this here is easy. However, you have to be careful. You're going to have to use u sub here, where u is 2x minus 1. Yes, du dx here will be 2, or we can say dx becomes du over 2. So this integral, natural log absolute value x plus 4. This integral here, when we do u sub, this is 1 over u, d over 2, and you factor out the 1/2, so it's 1/2 integral 1 over u, or we say 1/2 natural log absolute value of u, and then u here is going to be 2x minus 1. So these techniques here come into play, right? This is what we're looking at. So let's try to write this as a final answer, okay? Let's kind of do that here. See if we can fit this in. 4/9 1/9 times 1/2 natural log absolute value 2x plus 1. Yes, and plus that c. So let's write it clearly down here. 4/9 natural log absolute value x plus 4 plus 1/18 natural log absolute value 2x plus 1 plus c. So double check the work. You guys are really good at doing that. You guys are really good at double checking, finding a little bit of these the errors here. The coffee is starting to kick in. But this is actually your first method here, or your first way, your first case of partial fraction decomposition. Now remember what I always tell you guys. My job here in Calculus 2 is really 10% new, and your success is based on the 90% old. That 90% here is, with these two examples we've seen this morning, do you remember how to divide? Right? Do you guys know what I'm saying? Do you guys remember how to divide here? Divide using beginning algebra. The answer is yes. Thank you, Kirby. Do you remember partial fraction decomposition? And that's pre-calculus. The answer is yes, right? Now, when I took the course, just like you guys, I had to spend a lot more time reviewing, and that's normal. Because we don't know how long ago you took the course, or or what happened in that situation, right? So you're gonna have to do a little bit of reviewing there, and this is how we do that. Okay. All right, you guys okay with that? So this is the first case of partial fraction decomposition. Now I want to go back over here. Let's go back. I want you guys to recall where I said you had most work, and you go, okay, where's most work? See this equation here where all the work is? There's another way of finding a and b, and I want to go over that. So we have x equals, again, right, a, yes, times 2x minus 1 plus b times x minus 4. Okay, so here's something that we can do. So yes, this is 2x minus 1. Okay, good. So let's remind you guys, we want to find what a and b are. So let me show you. I'm going to put this little phrase then again. What is a and b? Well, I want you guys to go look at these linear factors here. Okay? Linear factors. We got this x minus 4. We got this 2x minus 1. I have to ask you guys, what values of x will make those equal to 0? So we want to make those linear factors 0. I'm going to start with the easier one. This x minus 4, I'm going to say, let x be the value 4. This is an equation, ladies and gentlemen, thought of as an identity. So if I plug in x is 4 here, x is 4, x is 4, x is 4. Notice what we get. 4 equals, is it x plus 4? Oh, thank you, Marbella. Oh my God. Got to go to the coffee machine. Got to start over here. Here we go. I'm going to ask a similar question. I'm going to ask you guys, focusing on the linear factor, focusing on this first linear factor. Let's ask you guys, how do I make that linear factor equal to 0? What value of x do I use? I'm focusing on the x minus 4. Let me get rid of this to keep you guys focused. What value of x makes that linear factor 0? What are we going to let x be? Let x be what? Negative 4? Double check. That linear factor is x plus 4. So we're going to put in that negative 4 here. Negative 4 here. Negative 4 here. Here's my point. On the left side, negative 4 becomes a times 2 times negative 4 minus 1. Really, not plus here. Yeah, plus, sorry. Plus b times negative 4 plus 4. Double check. So what happens now here, here's my point. We're making this linear factor here 0. Is that true? We want to make that 0. Isn't negative 4 plus 4 0? Doesn't that now mean b times 0 is going to be simply gone? It's 0. On the left, we get negative 4 is a times negative 8 minus 1. Or negative 4 equals a times negative 9. So when I divide now and I solve for a, and I divide by negative 9 for both sides, notice what we get. 4/9 is a because we had cancellation. We can also say a is simply 4/9. So double check. Isn't that the value we got before? A is 4/9? And the answer is yes. Now you might say, okay, you actually proved a point. We can let x be these values to determine what to get. We can. Now, if I go back to the original equation again, and you say, okay, you showed me how to find a. How can we find the other value, right? And I'm going to say to you guys, be careful here. Focus on this linear factor now. 2x minus 1. How do I make 2x minus 1 equal to 0? Right? So let's ask you guys, how do I zero out that a term so I can now get the corresponding b value? What do we let x be in this case? Anybody know? Because that's where we're at. what should x equal now? Right? I'm going to put this equation here. What would x be? Let me give you guys a little hint if you don't know. You're going to say, I want 2x minus 1 equal to 0. That's what I want. You set that equation. Oh, add 1. That means 2x is, is that what we have? Let's be for 2x minus 1, yeah. And then what do I do? Oh, 2x is 1. That means x is 1/2. So if we let x be 1/2 now, okay, we're going to let x be 1/2. So if x is 1/2 now, go back. 1/2 here, 1/2 here, 1/2 over here. You already know this portion will be 0. This is gone. Because 2 times 1/2 is 1, and 1 minus 1 is 0. So that now means when x is 1/2, notice what I get. 1/2 on the left side plus b times 1/2 plus 4. We can solve this equation. We can find b. So 1/2 now will be b. We'll do the arithmetic here. You guys know 1/2 plus 4. Do you guys know what that's going to give you? Isn't that going to give you 9/2? Double check that that's 9/2. Or we can say, if I start to write this equation, we can say 9/2 b is 1/2. Write it in a way that we're familiar with, the letter on the left side. Now we can divide both sides by 9/2 to isolate the b. So we'll get b will be 1/2 divided by 9/2. Or we can say b here will be 1/2 times 2/9, or b will be 1/9. And so sure enough, just like we did before, sure enough, we got the proper values of a and b. And that's done by zeroing out the linear terms. X is 1/2, x is -4. You could zero out those linear terms in the way that I just showed you. Okay, you guys okay with that? We can zero these out. So let's go back, and we have a couple of questions here. The questions here, first of all, the first thing that we know is we could create a system of linear equations based on beginning algebra. And then we actually have that way to go about this. The second equation, or the second question here we have, is whether this has a name. Well, it's referred to in a few ways. This is kind of a characteristic equation for the coefficients a and b. So you can use this coefficient equation here for these. But this is really methods that were learned back in pre-calculus, or I should say Math 260, partial fraction decomposition. So this is the 90% that I said to you guys was what you guys learned in your past. My part is to show you that 10%, that new 10%. So that's my answer for you guys here. You could use this characteristic equation, and that's the name, a characteristic equation for your constants. Or you could use Gaussian elimination, and now this is the same as it was. So here's how you handle what we call case 1. Now there's 4 cases, not just 2 cases. Okay, so you're going to look at this here and notice what I did this morning here. Okay, and I know I covered it up. These are linear factors. and they're called distinct linear factors, so they're different. So you can really pretty much set these up this way every time you see distinct linear factors. Now, we're gonna look at repeat linear factors. We're gonna look at quadratic factors, and we're gonna look also at what's called repeat quadratic factors, and then they have a combination of them. So there's gonna be a lot of work in this section, but the work is really something you guys already had back in those courses. So you're gonna remember, hopefully you can remember partial fraction decomposition. So that's your review, okay? Now I have a few seconds here with you guys, and you guys notice I do have office hours in Canvas scheduled for you. If you have any additional questions, you guys can actually come and ask. However, at this point, anybody have any questions so far on this? I know we only did a couple of examples, but we do have to go through the detail at first. And I will post a couple of more case ones for you guys as the examples on my website. And also I put them in Canvas so you guys know it's in both places. So at this point, anybody have any questions? Because I know it's Thursday and we lost a day, another day. But any questions on what we just did? I know there's a delay. Thank you, Morbella. I think Morbella's asking the question here. When's our first quiz? When I looked at, I put this in Canvas as well, right? I put that scheduled for not this week, next week. And the question is, what's people are going to say, what's on that? Well, everything that we had in the past, even before the break, up until pretty much what we conclude. And that's kind of what's happening here. So there you guys go. And I'll let you know, the school has gotten this proctorial software that they proctor exams, quizzes, whatever. And so, I'm going to have to wait and see what's going on with that. So that's what's happening. And I'll let you guys know, hopefully as soon as I know. But we're going to have to be flexible and open-minded. We're going to have to see what we can do. Okay, so that's going on, and that'll be next week. So work on those homework questions. We also have a question from Alexis here. Okay. That, Alexis, I can put the score in Canvas, and I'm getting what's called a special scanner, a fast scanner. So I'm going to try to look into maybe scanning that and sending that back to you guys. Okay, Alexis? So for your records. But what I'll also do is put this in Canvas, some of these scores for you so that you guys are up to date with all your scores. And, you can call them quizzes. You can call them tests. It doesn't matter. We're still continuing with what we're doing. But, that's kind of my take on it. It's how do we transition in this difficult environment, and it's not going to be a perfect transition. So I have some ideas about your testing. I think what you guys want to do, though, is make sure you definitely get started on your homework and all these techniques. And I'm going to give you additional homework just to get started. I mean, we haven't finished this at all, but I want you guys to consider that partial fraction decomposition in our book. Right, here's some of the homework. This section is 8.4. I would say, even if I said, 7 to 37 odd, as you guys know, I like even considering all of them, not just the odds. So you guys might want to think of that. So I hope I have answered some of your questions. Our first quiz, check the schedule in Canvas. It looks like it'll be like next Thursday, but I got to figure out how we're really going to do it. And I'll import your scores, Alexis, your test scores, right? I'll import that into Canvas so it's all up for you guys and up to date. So with that, if you have any additional questions, of course, you guys know I have office hours. I'll see you in Canvas, hopefully. And stay safe, okay? Take it easy. Of course, work hard. You got time at home. That's a good thing. And, I wish you guys well. So have a great day. And I'll see you or hear from you guys on, I guess Monday. Okay. So take it easy and take care.